central atoms attached. I'm sorry, there's no lone pair atoms. I apologize again. There's no lone pair electrons attached to the boron. So everything is nice and even and spread out evenly. Okay, in that case, nonpolar again. Even though it's not a straight line, all those terminal atoms are very even. Let's look at the next one. We have another one here. We've got a central atom and we've got 4 terminal atoms. And how are they placed? They're placed even. Why is it even? It's pretty much even because there are 0 lone pair electrons on the central atom. This is a big indication right here of whether or not it's polar or nonpolar. There's 0 here. Everyone's nice and pretty. This is also considered to be nonpolar. The next one, this is uneven. Remember, we try to make it even, but this right here, that lone pair shoved the iodines out of the way and moved them. And because they are so strong and they shoved them and they got pushed and shoved out of the way, an indication is if you do have a lone pair of electrons on the central atom, this is going to be a polar molecule. And then not only do we have 1, but we have 2. Okay? And both of those shoved, this one shoved the hydrogen and this one shoved the hydrogen out of the way and made them what we call bent form. And that is also polar. So to decide whether or not it's polar or nonpolar, there's a couple of ways. Number one, if you're given the numbers, then you can go ahead, do the math, find the difference, and look at the chart. If you're not given the numbers, then the next way is to go over here and do the molecular drawing. If you do not see any lone pair of electrons on the central atom, and everyone is nice and even and pretty, then it's going to be what we call a nonpolar molecule. Okay, meaning that one side of it's not stronger than the other. Okay, when you start to indicate and have lone pair of electrons on the Ca, then we start to call that a polar atom. Okay, or a polar molecule. Let's keep going. Polar versus nonpolar compounds, it says here. So compounds can contain bonds that have unequal sharing and still be what we call nonpolar. To determine if the compound is polar, you will need to determine if the spread of the electrons around the central atom is even or uneven. Remember, how is it even? It's even when there are no lone pairs. It's uneven when they do have a lone pair. Next part, it says here, if an electric charge around the central atom is equal, distributed, then the compound as a whole is considered to be a nonpolar. Okay? If the electric charge around the central atom is uneven, distributed, due to, listen to that, lone pair of electrons, or the different atoms being bonded from the central atom, and then the compound is considered to be polar. So a big indication is when you do the drawing, you can decide there whether or not there's lone pair or there's not lone pair. Okay? The other way, easy way, is if you're only given 2 atoms, then you can come over here, do the math real quick and see. But when you're given 3, 4, 5 atoms that are bonding together, then that's not easy just to do this math. It's easier to do the molecular drawing and then look to see how the electrons are distributed. Alrighty, so let's go ahead. It says here, draw the following covalent compounds and then determine, will this be a polar or a nonpolar compound? And the reason why we're going to have to do the drawings is because this one has 4 atoms, 3 atoms, 4 atoms, 5 atoms. Do you see what I'm saying? There's just so many atoms. It's not going to be a straight cut 1, 2, subtract it. Okay? So let's look at this part. First one, CO2. First thing I do is I'm going to, step 1, write down all of my atoms that I have in this compound. I have 1 carbon and 2 oxygens. Carbon is now step 2. Carbon is in what group? Group 4. We're still at step 2. Oxygen, what group is oxygen in? Group 16. So we're writing down the valence electrons for each atom. Okay, in step 2, after you do that, you add them all up. So 5, 10, 15, 16. That is the total number of valence electrons that needs to be distributed throughout the molecular compound that we're about to draw out, okay? The molecular drawing. So don't forget the rule. Every atom on the periodic table wants to achieve the octet rule. What are our exceptions? Boron, who only needs 6 valence electrons, and hydrogen, who only needs 2. Okay? So now that we did step 1, we did step 2, step 3 is to decide who is my Ca. Well, one indication is the one atom that is a single atom is going to be your Ca. So for an example, carbon and 2 oxygens. Carbon is going to be my central atom. Remember, our rule also said that carbons will always be the central atom. So I've got 2 oxygens. How do I draw them? I want to draw them as even and symmetrical as possible. So let's do an oxygen here and oxygen here. Okay? Now I've got to do one line here and one line there because they have to bond with each other. And the lines indicate sharing because this is a covalent compound. Okay? And when we do that, now I can see that 2, 4, subtract 4, now there's 12 valence electrons left over. Okay? What's going to happen here is that this is an oxygen. And remember, diatomic oxygen compounds or diatomic oxygens, they just like to have that double bond. Okay, that's what makes them so strong. Oxygen atoms, they're so strong because they have that, they like to form double bonds. So let's go ahead, and before we go any further, and before I do a double bond, I want you to also see why I'm about to do a double bond. Look at my Ca. When I look at the Ca, how many electrons are attached to it? 2 here and 2 here. So that's 4. I've got to have some more, right? I got to have 4 more because I'm only at 4. And carbon needs to have 8. Okay? So instead of putting lone pairs at the top here and here, what's really going to happen, because again, that's an oxygen, you're going to have a double bond that's going to occur. Now let's go back to this carbon. 2, 4, 6, 8. Carbon is good. So minus 4 equals 8. Now what's going to happen? Okay, are they going to bond some more and do a triple bond? No, oxygen can't do all of that now. He can't. He can make a double bond, but he cannot make a triple bond. So now I have 8 more valence electrons. My carbon is happy because he has 8. But look at the oxygen. He has 2, 4. Look at this oxygen. 2, 4. That's not good. They need to have more. They have to have 8. So 2, 4, 5, 6, 7, 8. 2, 4, 5, 6, 7, 8. Now I used up all of my valence electrons. Okay. My compound, my molecular drawing is very symmetrical, right? I can cut that sucker in half. It's nice and even and pretty. Okay. Is there any lone pair of electrons on the Ca? There's not. And because of that, that means that this molecule here is a nonpolar molecule. Okay. Did I do the math? No. The math is easy, but I can only do that when I have 2 atoms. I have 3 atoms here, so I couldn't do that. So let's go ahead and let's do the next one. Boron with 3 fluorines. Okay, remember our exception to the rule is when you have a boron atom, instead of having a octet rule of 8, he actually has 6. Okay, he's an exception to the rule. Step number 1, let's write them down. We have B, F, F, and F. Okay, go to the periodic table. Boron's in group 3. Fluorine is in group 7, group 7, group 7. We're going to add up all of our valence electrons, 5, 10, 15, 16, 17, 18, 19, 20, 22, 24. So 24 is that magic number. I need to distribute, forgive me, 24 valence electrons in this molecular drawing. Okay, so let's go ahead and let's do that. Now that we did this, what's our next step? Hopefully you're listening to me and the repeating's probably getting on your last nerve, but hopefully it's sticking in your head. The next step now is to decide who our central atom or our Ca. Remember, if you have a single element, he's probably going to be the Ca, and we have a single boron. So boron is going to go in the middle. I have 3 fluorines. Remember, we always like to be as symmetrical as possible. So let's go ahead and do that. Fluorine, fluorine, and fluorine. Okay? Now, it doesn't always be like that. Sometimes it's not always like that. Sometimes there's lone pairs that come into place and messes everything up. But at this moment, we try to achieve symmetrical shapes. Okay? Now, we have to use 24 valence electrons in the whole molecular compound here. How many electrons have we used? 2, 4, 6. So 24 take away 6 equals 18 left over. Okay? So before I go any further, could I add a lone pair of electrons on the boron? Cover up the F's. 2, 4, 6. Can I add a lone pair? No, I cannot, because boron can only max out at 6. So now those 18 are going to have to be distributed all the way around. So let's go ahead and do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now I used up all 18. There is no lone pair. There is not on my boron, which is my Ca. So in that case, then, this is going to be what we call a nonpolar molecular compound. So nonpolar covalent compound. Okay? So let's keep going. Let's look at this one. CH and a Cl. We're using 3 different atoms now from the periodic table. I like that one. Let's look at it. Step number 1. What do? We're going to write down all of our atoms: a carbon, 3 hydrogens, and a chlorine. And they're all going to be bonded together. Step number 2. Write down the valence electrons, which is the same as group number. Group 4, group 1, group 1, group 1, and group 7. Add them all up. 7, 8, 9, 10 plus 4 is 14. So 14 is the magic number of electrons that I need to add into my compound. Okay? Now I need to decide who is going to be my Ca. Is it carbon, hydrogen, or chlorine? Remember the rule. Hydrogen can never be a Ca. They can only be terminal atoms. Okay, so in that case, it definitely can't be the hydrogen. Now we're down to the chlorine and we're down to carbon. Okay, but the next rule from our notes is when you look at the periodic table, chlorine is over here and carbon's over here. Carbon is further to the left of the periodic table, so he is going to be our Ca. So let's do that. Carbon goes in the middle. Alrighty. Now, what else? We have 1, 2, 3 hydrogens and a chlorine. What do we like to do? We like to draw it as symmetrical as possible. So let's do that. 1, 2, 3, 4. Hydrogen, 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 and then a chlorine. Okay? Now we've got it all in here. It's nice and even, symmetrical. I like that. We still have used up 2, 4, 6, 8. We used 8 of those electrons already. Okay? So that leaves us 6 left over. Let's go back to the carbon. That's our Ca. How many valence electrons can carbon hold for to achieve the octet rule? 8. 2, 4, 6, 8. So that means that can we add any of those 6 that are left over onto the carbon as a set of lone pair of electrons? No, I cannot. What is the rule about hydrogen? The max they can contain is 2. This hydrogen has 1 line, so that's 2 valence electrons. So he cannot have any more. This hydrogen has 2. He cannot have any more. This hydrogen has 2. He also cannot have any more. So that means that chlorine is going to take the leftover. How many leftover? 6. 1, 2, 3, 4, 5, 6. And let's make sure that makes sense. Cover everything else up. Chlorine, what is the number of valence electrons he must have to achieve the octet rule? He must have 8. 2, 4, 6, 8. Bam. We're perfect. Subtract 6 equals 0. Done. Okay. Now let's look at this. Are my electrons distributed throughout the whole compound evenly? That's what you need to ask yourself. Okay? If the electrons are distributed around the molecular compound evenly, is it or is it not? Stop and look at it for a moment. I mean, line, 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 line. That's nice. But look at this. 2, 4, 6. No extras, no extras, no extras. Remember, the quick and easy rule is to look at our Ca. And if our Ca has a lone pair of electrons, then bam, it's going to be polar. When it doesn't, and we have something like this a little weird, then we ask ourselves, are the valence electrons distributed around the whole compound evenly? If not, because look at them, they're all, hanging around chlorine, okay? Then that means that this is going to be a polar molecule, okay? It is going to be polar because it has more electrons over here. It's going to have that stronger pull towards it, okay? So you've got one here to do, one over here to do, and one over here to do. So you need to do the drawings for those 3. You need to decide whether or not it's polar or non-polar. Again, practice is what's going to help us get better at this, because I know we're getting into some new stuff that you probably have never seen or heard before. Let's turn this page. And the last part here talks a little bit about polarity, okay? So just in general, what polarity is and kind of like what it means. So it says here, polarity within covalent compounds or covalent bonds though. When atoms unequally share the electrons in the bond is called a polar bond or a polar covalent. When atoms equally though share the electrons in that bond, then the bond is called nonpolar. The unequal sharing is based on the electronegativity of the atoms involved in the bond. The atom with the higher electronegativity attraction attracts the electrons more, okay? Remember that fluorine has the highest. Remember flossy fluorine? So remember that fluorine has the highest electronegativity. And the electronegativity increases going to the left, to the right, across the periods, and decreases from the top to the bottom in the groups. Okay, so with that, and we've already talked about this last unit, which one here is going to be, it says here, which atom in each bond attracts the electrons more? Who's stronger? Well, first thing is, I definitely know that flossing fluorine is, right? And if I had to look over here between hydrogen and sulfur, sulfur is closer to fluorine, so sulfur is stronger than hydrogen. Chlorine and chlorine. Whoa. What about that? If I've got two of the elements that are exactly the same, is somebody going to be stronger than the other? It's like having twins. They're the same. Okay? So there's nothing is stronger than the other. So let's keep looking. Nitrogen and oxygen. Oxygen is closer to fluorine, so this bond or the strength is going to go this way because oxygen is stronger. It's going to pull this way, and it's going to pull this way. Is there going to be any pull with the chlorine and chlorine? No pull. So we call that non-polar. Because there's not, one of them's not stronger than the other. They're exactly the same. They cancel each other out. You can think of it that way. Now, We'll come back up here in just a moment. For a molecule, the molecules are either going to have a polar or a nonpolar, depending on the covalent bonds they contain and the molecule's shape. A polar molecule has a partial positive charge and a partial negative end charge. So for an example, it says here H2O or water. You've always seen it like this, but now why is it like this? Water molecule looks this way because it has two lone pair of electrons on the oxygen. So each molecule of water has two hydrogen and it has one oxygen atom that are covalently bonded together, right? Why is it a covalent compound or covalent bond? Because both of those are going to be nonmetals and nonmetal, okay? But water is a polar molecule. The oxygen end of the water molecule tends to pull the shared electrons away from the hydrogen atoms so that the oxygen end has a partial negative charge and the hydrogen's end have a partial positive charge. The bend structure also affects the polarity. The two lone pair are near the oxygen end, increasing the partial negative charge. Okay, so let's go back and let's look at this. Here's our compound over here. We've got two sets of lone pair of electrons. One set of those electrons are kind of over here, like at the top. The other set is in the back behind the oxygen, but I can't draw it in the back, and I have to draw something so we can see it. So I'm going to draw them down here, but they truly are behind this in the back of it. Okay, they're attached in the back end. Now, let's go ahead and let's look at this. If oxygen has all of these extra lone pair of electrons, it has a little bit stronger negative end compared to the hydrogens. Do they have extra negative electrons hanging around them? No. So because of that, they end up being on this side what we call partial positive end, and the oxygen side is a partial negative end. Those are called, the little symbol is called a sigma, and you saw that on the video notes. So the sigma end here is a partial negative, and the sigma end here is positive, and this one is positive. It looks like an 8 almost, okay? This tells me that the oxygen with those electrons is a little stronger and is pulling the hydrogens towards it, okay, unevenly. Now also though, if we go back to the previous page with our little chart over here, let's look at oxygen. Oxygen's 3.5. So I'm going to write over here 3.5. What is hydrogen? 2.1. 2.1. 2.1. And I can see that with that stronger electronegativity, it pulls it unevenly towards the oxygen. Now it says here, why is this important though? It's important because the polarity of water actually makes it extremely effective, what we call solvent. It dissolves many other polar substances to make a solution. In fact, water can be described as what we call the universal solvent. Like test question. Universal solvent. What is a solvent? It dissolves things. Non-polar substances, such as like olive oil, are insoluble in water. A common expression used is like dissolves like, which means if water is polar, then if we have other substances that are polar, water can dissolve it. Okay? So this means that polar substances dissolves other polar substances, and non-polar substances dissolves other non-polar substances. Okay? Now, before we go to the next set of our notes, we have a little bit more. Okay? I just want to make sure that I'm going to write it over here. We are going to get into what those shapes are a little bit more with that lab We're also going to have some videos to kind of help us understand those shapes a little bit more. But one thing that I do want to write for us is when it comes to the shapes of the polar and nonpolar, I'm going to write nonpolar. When they're nonpolar, remember they're symmetrical. They're even all the way throughout. Symmetrical. Okay. Here are some of the shapes. When they bond, if it's a linear shape, it is nonpolar. If it is a triagonal, planar, it's also a nonpolar. If it's a tetrahedral, so in our notes, there are more shapes. Where are all of our shapes going to come from? That's going to come from that computer lab that we have. If it's a what we call octahedral, then it's also going to be nonpolar. If it's a square, planar, it's also considered to be nonpolar. Now let's look at the ones that are considered to be polar. So polar, and remember polar is what we call asymmetrical. Okay, and asymmetrical, bent, like water. Pyramidal are going to be also asymmetrical. All right, so hopefully you're able to see those. Let me go back over here, pause it so you can write those in, pause it so you can write those in. You are going to see more of those names when we do the computer lab, okay? We're not done. We're almost done. We're almost to the naming part, okay? So I'm going to pause here and come back and video some more later on, but I want to at least get to this point with us.